for you to what? Understand. Okay, that's the most important thing. Complex stuff does not need to be what? Complex. It can be what? Simple. Okay, we just need to find time. Okay, avoid my daughter when she's crying and pretend to work, let the wife handle it. That's how I do it. Okay, okay. Now let's do another example. Anyone, any question online? Anyone, any question, please? Anyone? Oh, sorry. I can see online. There's a question. Why, Jihan, why don't we multiply the web by 2? That's what Jihan asked online. And on the web, I don't multiply by 2 because we are only going to consider the right-hand side. Jihan, does that make sense to you now, please? Jihan asked why we don't divide this, we don't multiply the web by 2 down here. Okay, because the left-hand side and the right-hand side are not related. Okay. Okay, Jihan, understand. You all have any questions? Yes. We will look at the final answer then. Okay. Yes. Say it again. Good question. When symmetric, all this will fail. Because when it's not symmetrical, which we will teach in week 6, Wednesday. When it's not symmetrical, it will twist. Because why? That's a good question. What if now, oh, too excited now. I need to come down with drugs. That's what my wife always say, okay, Eugene, calm down. We need you to calm down or not. Let's say now your structure is like this. Okay? And then we apply a force down here. Right? We apply a force down here. Okay, now we have a structure like this, and we are going to apply a force down. Now, question for you. Which side is more rigid? Right? The left-hand side is more rigid, or the right-hand side is more rigid? The right-hand side will be more rigid because it has a deeper what? Depth. Yes or no? First moment of area is a y bar. Right? So if we look at this side will be more what? Rigid. This side will be less what? Rigid. When this happens, you can do this at home. Okay? When this happens, you will have a what? Rotation. When you have a rotation, whatever we do down here goes to the toilet bowl. Does not work at all. Okay? But on week 6, next week, Thursday or Friday, I'm going to teach you how to analyze a structure like this. Okay? Good question. Okay? Right. So now let's look at the next example. Anyone, any other question? No?
I have a question.
Yes.
So if this was not a thin wall like shear problem and we were analyzing like a box beam like this, like the way we did before, we would consider both sides, right? Like we would take 2 times the thickness.
Yeah, you also still take the 2 times, Matthew. You're right. Okay.
Thank you.
Okay. Let's look at our next question. Where is it now? Yeah. My favorite. Okay, so as I said, you can get all this on Avenue to Learn. All these images are there. Okay, very similar concept. Okay, the question is very similar, only the structure is different now. Okay, so look at this. Knowing that a vertical shear V causes a maximum shearing stress of 75 megapascal in an extruded beam, having the cross section shown, determine the shearing stress at the 3 points indicated. Point A, point B, and point C. Okay, so for this case, it's doing two different analysis. Okay, so what is the difference? Okay, so the difference is this. Okay, so I'm going to copy. I'm going to paste this elsewhere. Okay, so what is the difference? So anywhere from here to here, anywhere above this line. Now this is not the what? Centroid. This is not the centroid. Anything up here, we are going to do thin wall analysis. Okay. Then I'm going to draw our centroid. Because of the rules that we don't cross the first moment of area, I mean, we don't cross the centroid for first moment of area. Anywhere in this range, we do not thick wall. I described to you as non-thin wall. Okay, so anything above this, can you all see color? Is there color? Anyone? Right? What color is it? Up here, red, right? Okay, thank you. Anything up here, we're going to carry out thin wall analysis. Anything in between there, right? We're going to carry out non-thin wall analysis. Okay. Now, some of you will ask me, Eugene, now I'm in the real world and I don't have you beside me and I got my degree. How do I know when to use what? What? Yes or no? My answer to you in this is two answers. If you're not sure, do both, especially on the top part. If you're not sure, on the top part, do both thick and thin wall analysis. Pick the one that has the what? Higher stress. Second option, give me a call, okay? And I'll tell you also, okay? Just email me, just fax me the diagram, and I'll say, okay, thick wall, thin wall. Are we clear? Okay? So if you're not sure, Eugene, how do I know there is thin wall, there is thick wall, okay? You do both. Yes. Yes. Okay? You calculate based on a higher stress value. Okay? And you justify why. Okay? Don't just go. Okay? You make your assumption. Okay? So that's what we're going to do now. Okay? So again, we are still going to do everything is the same. We are number one thing we're going to do is we're going to design the what? Shear flow. Yes or no? We're going to design the shear flow. And what controls the flow of the shear flow? The web. Yes or no? Right? So the web to me is what I'm going to sketch now. Okay? So this section is my web. Okay? And then this is where our Vy comes. Okay? Our Vy is coming from top. So the web controls it, and then we're going to design our Q. Okay? Then we do this. So this is our terminal, our terminal, our terminal, and our terminal. Right? Okay. Now we know. Okay. So now, after you design, then things are very clear or not. You're like thick wall or thin wall. Okay. Okay. So now we are going to look at the formula going to use is the shear stress is equal to Vy over Izz, okay, Qz divided by T. Formula is always the same. Am I right? Right? What formula? Right? I told you, right? This course, the interesting part is this. Two formulas you can apply in a lot of different situations, but there are 6 rules or 7 rules that you have to what? Comply. Okay. So now, Vy and Izz are constant. So the thing we have to find Qz. So at point C, so now we are going to find point C. Okay. The point C. I'm going to use this because I want to show you where is the area that we're going to consider. Okay. Because for the fact that the left and the right is a white flange, okay, the fact that we are going to find shear stress, okay, at point C, right? At point C, and at point C, right, we are going to have a white flange, okay, white flange analysis. There's only one Q, and the thickness we can see. The thickness is, I think all these are in millimeters, is 0.001, no, 1, 2, 3, no, 0.1 meter. Okay, it's one Q only because it's what? White flange analysis. So this is the area that we're going to consider. Okay, that's the area we're going to consider. So when we will consider the area, so that is your Q. So so your width will be what? Your width will be, pardon me, okay, your width will be 30. Your depth will be 10. That will be the Y bar. Sorry, this will be 10. The Y bar will be 160 divided by 2. This is half minus by 10 divided by 2. So this will be equal to 160 divided by 2 minus 5 times by 30 times by 10 is equal to 22.5 times 10 to the power 3 millimeter cube. Let me do it again. 160 divided by 2 minus 10 divided by 2 times by 30 times by 10 is equal to 225 times 10 to the power 3, correct? Or 22.5 times 10 to the power minus 6 meter cube. Okay. So from here, we just need to now find the shear stress at point C is equal to Vy over Izz multiplied by 22.5 times 10 to the power minus 6. The thickness now is 0.01. Okay, and multiply by 1, this is because we only have what? Q. Okay, because the Q on the left-hand side, the Q going towards the left and the Q goes towards the right starts from 2 separate terminals. So that's why you don't combine them. Okay, that's why. So it's equal to 22.5 power 3, 22.5 power minus 6 divided by 0.01 divided by 1 is equal to 2.25 times 10 to the power minus 3, okay, Vy over Izz. Okay. Now, some of you will realize that, Eugene, now I'm beginning to write shear stress at point C. What is the direction of the shear stress? Right? What is the direction? So I'm going to expand a bit regarding the direction. Okay, I want you all to watch this. Oh, I do apologize. Please finish copying first. Okay, I do apologize. So I'm going to draw a transformation over here. So this is our Y, this is our Z. Okay, right. So we know that this plane right, intersect the x-axis on the transformation. Okay. So when we draw the shear flow, so the shear flow goes this direction over here. Down here go this direction. Down here come down this direction. Down here go this direction. Over here this direction. Okay. So at point C, this is equal to the shear stress, right? The intersecting plane is X. The shear flow is in what direction? Can you see the Q down here is in what direction? Z direction, yes or no? So this is Z at point C. Okay. Now let's focus at point D now. Okay, so this is our point D down here. B. Sorry, B. Okay, that's our point B down here. So this is our shear stress. The intersecting plane is still intersect the x-axis. Now the shear stress go in what direction? Y direction. Okay. Now you see the difference. I did not include it earlier. I don't want it to be too messy for you guys. Okay. On that note, I'm going to stop here. I will see you guys on Friday. Now on Friday, lecture will start from 8:30 to 9:20. Then we'll carry on from 10:30 to 11:20. And tomorrow, good luck for your thermodynamics. Try to remember stuff, okay? Right? I know remembering is quite a challenge. I'll see you guys on Friday then.